having given you the concepts of first moment of an area and the concept of centroid, we are now ready to apply these concepts to mechanics. So, the question we ask is, suppose I have a beam on which I do not apply force at a certain given point, but the force on it is distributed. So, there is some force per unit area. Let me show this by a graph, per unit length. So, there is a force acting at each point. Let me call this function f x, so that if I take a distance, a small section of length delta x here, the net force acting on this point delta f is going to be given as f at x delta x. What we wish to now find is what is the net force acting on this beam and where does it effectively act. That means, if I were to suppose apply an opposing force to balance it, where should I apply it so that this force is balanced? The answer comes in terms of the quantities just defined. So, if there is this force f x, distributed force acting on it, the beam, the net force F is going to be summation delta F, which is nothing but summation. Delta F is nothing but f x delta x, and this is nothing but integration f x dx, which is the area under this curve. That gives you the total force for a distributed force per unit length given. How about the moment or the torque created by this force? That is obviously going to be x delta f integrated, which is nothing but x f x dx. This is the torque. If I want to apply an opposing torque with a point force, that force has to be equal to the net force which is being applied, which is the area of this curve, and it has to be at a point x, which is nothing but integration x f x dx divided by integration f x dx, which is nothing but the centroid of this curve that describes force per unit length. So, we can say that effectively the force acts at the centroid of this given area, which describes the force distribution. So, you see immediately the connection between the first moment or the centroid that we define with a problem in mechanics. As an example of things to come, let me end this lecture by solving a problem of calculation of the center of gravity of a rod made of two different materials. So, we take a rod which is made of two different materials. One material here is of length L1 and its mass per unit length is lambda 1. The other rod here is of length L2 and its mass per unit length is lambda 2. We wish to calculate its center of gravity. Starting from this point, let us say this is our axis, so that this is our x axis, this is our y axis, or on the y axis I will be showing the load, and this is x equal to 0. Let me go to the next page and show this rod, black here of length L1 and blue part for the other length L2, L1, mass per unit length is lambda 1 here, lambda 2 here. My axis is starting from here and going this way. If I plot the load curve, it will be constant lambda 1 g per unit length here, and if we assume lambda 2 to be greater than lambda 1, lambda 2 greater than lambda 1. And I wish to calculate the center of gravity. By definition, the center of gravity is the centroid of this load curve. So, this is going to be lambda 1 g is the load per unit length in the first part times x dx integration 0 to L1 plus integration L1 to L1 plus L2 lambda 2 gx dx divided by the total area, which is going to be lambda 1 L1 plus lambda 2 L2 times g. You see, g cancels from the denominator and the numerator, and I am left with the center of gravity of this rod L2, L1, lambda 1, lambda 2, and let me again show you the load curve is something like this. The center of gravity is 0 to L1 x lambda 1 dx plus L1 to L1 plus L2 lambda 2 x dx, g we have already cancelled, over lambda 1 L1 plus lambda 2 L2, and this comes out to be lambda 1 L1 square divided by 2 plus lambda 2 1 over 2 L1 plus L2 whole square minus L1 square divided by lambda 1 L1 plus lambda 2 L2. You simplify this and you get x c, which we just calculated to be 1/2 lambda 1 L1 square plus 1/2 lambda 2 L1 plus L2 square minus L1 square over lambda 1 L1 plus lambda 2 L2 to be 1/2 lambda 1 L1 square plus 1/2 lambda 2. I can simplify this. This will come out to be 2 L1 plus L2 times L2 divided by lambda 1 L1 plus lambda 2 L2. So, from the left hand side end of the rod, this is where the center of gravity lies. We can also calculate the center of gravity by using our observation earlier that if there are two different areas given, the center of gravity can be calculated from those two if I know the center of gravity of each one of them. So, if I were to use that, you see the load curve on the rod is something like this. I know the center of gravity of this load, which is like here at a distance of L1 by 2, and center of gravity of the other load is here, which is at a distance of L1 plus L2 divided by 2. The total area here is lambda 1 L1, total area here is lambda 2 L2. So, x c is going to be x c 1, that is the first part, times area 1 plus x c 2 area 2 divided by area 1 plus area 2, and that is going to be L1 over 2 times lambda 1 L1, g would cancel from the top and the bottom, plus xc2, which is L1 plus L2 divided by 2 lambda 2 L2 over lambda 1 L1 plus lambda 2 L2. So, we have calculated xc to be lambda 1 L1 L1 over 2 plus lambda 2 L2 L1 plus L2 over 2 divided by lambda 1 L1 plus lambda 2 L2, which is same as lambda 1 L1 square divided by 2 plus lambda 2 over 2 L1 plus L2 times L2 divided by lambda 1 L1 plus lambda 2 L2, which is the same answer as we obtained earlier when we calculated the center of gravity by integrating over the entire area. So, this is a simple example of how center of gravity is related to the centroid of the load curve. In the next lecture, we will be doing more such examples.